All right, so this is the beginning of the end. This is the first lesson in the last part of this course, which is looking at differential equations, which will complete the entire HL part of this course. And most of this lesson here is first looking at an introduction to differential equations, some terminology, and then the beginnings of how we work with these equations. All right, so let's just look at this. One thing we want to be aware of is what it means to describe the order of a differential equation as whether if it's linear or nonlinear. So the order is pretty easy. The order of a differential equation is the highest order of a derivative in terms of the dependent variable here. And so these are all the dependent variables, all y. And maybe I should say even before then, a differential equation, which we have seen a few times in the course, is an equation in which the derivative of the dependent variable is part of the function. Everything you see here is a differential equation. Notice this first question here, this first equation. We have the derivative of y as well as function y and function x all hanging out together. And that's something we've just seen the tiniest bit of before, and they can get really quite complex quickly. We'll go a little ways with it over the next few lessons. So the order of this is a first order differential equation because the highest derivative we see is the first derivative of y. So this is a first order differential equation. Quite often, I'll just say first order. That's it. It's also, is it linear or nonlinear? A linear differential equation is one in which all the dependent variables, which is y, are of a linear nature, like y to the power of 1. In this case, I can see that's y to the power of 2. So this is nonlinear. So it's a nonlinear first order ordinary differential equation, but let's just focus on the first order and nonlinear. All right, the second one is the second order differential equation. This one is linear. Notice I have y to the power of 1. I have the derivative, but times x, and that's it. That's all good. And so this is a second order differential equation, but it is linear. Or it's a linear second order differential equation. This one here is a first order differential equation. But is it linear or nonlinear? There is a sign function here, but there's x inside it, not the dependent variable. If we look all through here though, right here, it looks like it's linear. But right here, if I was to distribute this out, at one point I'd have y times the derivative of y. And while one's a derivative and one's y, that does make it nonlinear. So this is a nonlinear first order differential equation. If I look at this fourth one here, this is a third order. Fancy. Is it linear or nonlinear? It is linear because if we look, we have x times the derivative of y, we have 7 times y. We don't ever have y times itself or y times its own derivative. And so this is linear. Lastly, it's definitely second order. I can see from that second derivative. It is also non-linear for a similar reason. I'm forgetting how to speak. We saw before, it's right here. This is y times its derivative. It's the same reason in example 3 it was non-linear. You had y times its derivative, so it's non-linear. That's it. Don't expect a lot of questions about that, but we are meant to kind of know the difference between different orders and if it's linear or non-linear. That's it. Most of what I want to talk about today is the idea of separating differential equations, and sometimes they can't be separated, what that means, and how we can use that to find the solution of a differential equation and what that means. And there's different types of solutions. So maybe I'll start with up here. In general, if a first order differential equation, and we're only going to deal with first order differential equations now, at least for the time being, it is separable if there's a way of writing it like this. If you can have dy dx on one side, and the other side you have a function of x times a function of y. So if there's a way to write it like that, the derivative of y on one side and some function of x times some function of y as a product, then it's separable. Otherwise, it's not. And so if I look here, is this separable? Is there a way to write it like that? Well, if I just multiply both sides by x, I really quickly get to just y prime on one side, or I'll write it as dy dx right now, equals x times y. I have the derivative on one side, with, derivative of y with respect to x on one side, times a function of x and a function of y, just x and y. So this is indeed separable. So if it's separable, now what I want to do is I want to write them in a way that I could use to determine the general solution. So what I want to do in a moment is, I'm not actually going to find the general solution for this question, but I want to find a way to set it up so that I could do that. So the basic idea to this is I want to take my equation now that it is separable. I can see it's written in this form. And I want to isolate all my y's on one side and all my x's on the other, including my dy and dx. So in this case, you can imagine me multiplying both sides by dx and dividing both sides by, or maybe I won't say dividing both sides by y. Multiply both sides by dx and multiply both sides by 1 over y. Yeah, I know that got messy. And if I do that, what do I have? On the left-hand side, I have 1 over y times dy. On the right-hand side, I have x times dx. So now this is in a form that we can integrate fairly quickly to find the general solution, which again was part of a later question. And this sort of form here, I believe, I have a little note about it. If something is separable, we should be able to write it in this form, where we have whatever function we used to have up here, we now have the reciprocal of it here, times just dy. Whatever function we have here is now being multiplied by dx. And then in a bit, we'll see how integrating that is actually can be relatively quick. All right, so I've got that first one done. The second one, is this separable? Nope, it's not. And now it's hard to tell right away. For example, if you add x to both sides, I get dy dx on one side, and I get y plus x on the other. That's a sum of functions. I want a product. Although sometimes through factoring, we can make a product. But no matter what we do, we can't make this right-hand side a product of a function of x and a function of y. For example, I could take out a function of y. Take out a factor of y. If I do that, I get 1 plus x over y. This here is still a function of x and y. So no matter what I do, I can't find a way to write the right-hand side as some function of y times some function of x. So this is not separable, which means nothing else to do there. Let's look here. I have a sum on the right-hand side, but like I said, quite often through factoring, we can separate things. And in fact, if I just right away take this, and I'll write y prime as dy over dx. If I take out that factor of x, I now see I do have a separated differential equation. On the right-hand side, I have a function of x times a function of y, which means I can now write it into this sort of form we did up here, where I want to divide both sides by 1 plus y, or write 1 over 1 plus y times dy on one side, multiply both sides by dx, I get x dx on the other. All right, so for this last one, again, is this separable? First, I have, it's a little bit messy looking here, but if I divide both sides by root 1 over x squared, I'll write that right here. Then I have just my derivative with respect to x on one side, and I have 1 plus y squared over the square root of 1 minus x squared. All right, I need to make a product here. Well, as we've seen before, anytime we are dividing by anything, we can write it with a negative exponent. So I can write this as just, I'll do the y first. Doesn't really matter the order. 1 plus y squared times 1 minus x squared to the power of negative 1/2. So notice now I do have what I want. I have separated the differential equation into one side having a product of a function just in terms of y, the other is a product of a function just in terms of x. So now I want to rearrange it to put it into a form in which I can integrate quite nicely. In this case, I would get 1 over 1 plus y squared times dy on one side, and I'd get just 1 minus x squared to the power of 1/2 dx on the other. All right, that said, now let's actually look at finding that general solution. I keep saying once we're at this stage, we can then integrate both sides and use that to find a general solution. So that's what these questions are about. So determine the general solution for each of the following. Well, first, I gotta separate the variables. Well, they already are separated. In fact, if you look right here, this is what we have up here, which means I can kind of copy my steps here and take this function that I've circled and let me write it first. I can write it as 1 over, don't you move on me, screen. So I'm going to divide both sides by y, so I get 1 over y times just dy. On the other side, I'm also going to multiply both sides by dx. You can think of it that way. And so I have this. Now that's the same answer I had from the previous question. But now what I want to do is I want to integrate both sides. I want to find the indefinite integral of both sides. Notice on one side it's with respect to y and one side is with respect to x. So if I look at this now, I have this is the antiderivative of 1 over y is the natural logarithm. So I have the natural logarithm of the absolute value of y plus some constant. On the other side, I have the antiderivative of just x, which is 1/2 x squared plus some other constant. I'll put c2 and c1. Now at this point, I'm going to make some changes. Having two separate constants isn't wrong, but it's kind of silly because they can be really right now any number, which means I could subtract c1 from both sides and put them together, and I have one constant minus another. I could call this c3, or in the end, what I'm going to do is just erase this. Oh, not erase all of that. Erase this constant here, and I'll call this just constant c. And keep in mind that is meant to represent those two constants put together. Or maybe I'll just call this c1 now, because actually I'm going to have another constant in a bit. All right, at this point, I now need to find the general solution. I need to solve for y. Now at this point, if I look at my absolute value brackets here, I know that function y here, as long as y is positive, we're okay. And quite often, as long as we don't forget that the natural logarithm can't have a negative inside there, quite often we just move on and just think of this as the ln of y. So I have the ln of y equals 1/2 x squared plus this constant. If I solve for y, I raise everything from to a power at the base of e. And so this becomes just y equals e to the 1/2 x squared plus c1 up in the exponent still. That said, if I look at my power here, and we're going to see this a lot, I have 1/2 x squared plus some number. That's the same as, thinking about our exponent laws, that's the same as e to the 1/2 x squared times e to that constant. And again, c1 is just some number. And so e to the power of c1 is just some constant. It sure looks like a g right now. But that's some constant. And so instead of adding more and more little 1s and 2s and 3s to my c's, I'm going to write this as y equals, I'm going to put that first, but just call it c. That's just some constant. E to the power of some number, I'll just call that c, times this part here, times e to the 1/2 x squared. And this is what we call the general solution to this differential equation we gave here. This is our general solution. And a general solution will always have some sort of constant in there. Notice as I integrated and did a bunch of work here, I had multiple different constants, but in the end, I only needed to have one constant here. And so I'm going to leave my final answer with just c instead of c1 or c2 or something else like that. All right, so that's the general solution. Let's do something similar for this. It already is separated. That's very nice. It's already separated, so now I need to rearrange it a bit and put it into a form that I can integrate, which means I'm going to divide both sides by y squared. So I have 1 over y squared times dy on one side, multiply both sides by dx. I have x dx on the other. I'm going to find the indefinite integral of both of these. And so if I do that, On the left-hand side, that's 1 over y squared is like y to the negative 2. Find the antiderivative of that. That's negative 1 times y to the negative 1. I'll just write negative y to the negative 1. Again, plus some constant that I'll call that constant, I could say constant 1, but at some point, that's not really going to matter because on the other side, I have 1, same thing as before, 1/2 x squared plus some other constant. I could call it constant 2, but I'll just put these two constants together, and I'll call it constant 1. That's it. I can denote it whatever I want. All right, I now want to solve for y. So let's think what I have on the left-hand side here. That's the same as, first let me multiply everything by negative 1. So I have just 1 over y on one side, and I have negative 1/2 x squared. I could say minus c1 over here, but again, that constant can be any number, positive or negative. So it's, I shouldn't get too hung up on plus or minus there. So I'm just going to stick with the plus. And if you don't like that, I'll call it c2 now. Okay, it's just some constant. But I want to isolate y. So before I do that, you may be tempted just to flip everything over. However, to do that, I really need to quickly find a reciprocal. I need to make this here one term. And so I'm going to rewrite this here, find a common denominator, and I get negative x squared plus 2 times that c2 all over 2. That's 1 over y. So that's finding my common denominator, because once I have one single fraction, the reciprocal is just flipping everything over. That means my general solution, y, is 2 over negative x squared plus 2 times this constant. So I want to clean this up a little bit. While this is correct, keep in mind right here, this constant, like I keep mentioning, is important, but the actual number can be literally anything. So I'm going to rewrite this as partially as 2 over, I'm going to put plus just a c now, instead of 2 times some other constant. And again, this minus x squared in the denominator, I'm going to write it as just positive x squared and have the negative up here. I just like the way that, I like that a bit better. Again, it does not matter. We cannot assume that constant as well as a positive number, it may be a negative. But this, again, is what we call the general solution to this differential equation. Which leads me to the last part, which is what's a particular solution? A particular solution is essentially the same work. You get to the general solution, but you should be given some sort of a condition that allows us to figure out what that constant is. So if I look here, I have a differential equation, and we want to find the particular solution at this point here. That'll actually be the last thing I do. Most of my work is everything we've done before. So let's look at this equation first, and let's make sure we can separate the variables. And so let me just copy down this equation right here. So I have xy prime plus y prime equals 1 plus y. So I'm going to isolate y prime. I'm going to factor it out. I'm going to now isolate the y prime. Maybe I'll save myself a bit of space here, write it sideways. So I have y prime, which is dy dx, equals, on the other side, I have, what do I have here? I have 1 plus y times 1 over 1 plus x. All right. That said, that's now been separated. So now I want to get ready to integrate it, which means I actually want that 1 plus y. I want to divide both sides by that, and multiply both sides by dx. So that leads me to this. That leads me to 1 over 1 plus y times dy on one side, and 1 over 1 plus x times dx on the other. And now I want to integrate each of these. All right, if I look at each of these, I can tell these must both relate to the natural logarithm. In fact, if I look at that, the antiderivative of that would be the natural logarithm of 1 plus y, or the natural logarithm of the absolute value of 1 plus y. And so something similar on the other side. So I have the natural logarithm of 1 plus y plus some constant equals, on the other side, the natural logarithm of the absolute value of 1 plus x plus some constant. Again, instead of having two separate constants, I'll just put them together here. At this point, unless we have, the absolute value, we'll just, going forwards, we will assume that we're just dealing with numbers that don't give us something that leads to a problem in our natural logarithm. We're not going to put -2 into x. And so I'm now going forwards, I'm going to think about just the natural logarithm of 1 plus y and the natural logarithm of 1 plus x plus this constant. Raise everything as a power to a base of e, then I have just 1 plus y on one side, and I have e to the natural logarithm of 1 plus x plus this constant on the other. Subtract 1 from both sides, and I get y equals e to the natural logarithm of 1 plus x. Now at this point, like we saw before, instead of adding this constant of c1 in the exponent, I'm going to write it as multiplied by e to the power of c1 right here, and then minus 1 from this, because I subtracted 1 from both sides. And that constant of e to the power of c1, I'm just going to write that now as just c. And so this leads me, I'm running out of space here, this leads me to y equals e to the natural logarithm of 1 plus x, which actually I'd save myself a bit of time. Those are inverses of one another, so let's just save myself the time and the space and write 1 plus x times this constant c, which I can put first or last, it doesn't matter, minus 1. So again, that's my general solution. 1 plus x times c minus 1, or it's probably a little more conventional to put the c first. That is the general solution. But we want the particular solution, knowing that y of 1 is -2, which means when x is 1, y is -2. Well, let's go back here. When x is 1, y is -2. So now I can find the particular solution by using that fact and writing off the bottom of my page. -2 equals c times 1 plus 1, take away 1. Because again, it tells us in the question, when y is 1, so when x is 1, y is -2. And then I can quickly solve for c. It takes very little work to get that c must equal -1/2. So now I know my particular solution. So I can say, okay, I'm going to take this 1/2 and put it back right here. And since I have an endless screen, I can just write and say that my particular solution which is only true when y at 1 equals -2, right? Specific to that, the particular solution will be y equals -1/2 times 1 plus x, or x plus 1, take away 1, which is a linear function. If you want, it's not hard to distribute the -1/2. I get -1/2 plus, actually, if I just combine like terms, I'll save the time. We get -1/2 x minus 3/2 if we just clean this up a little bit. So again, that's a particular solution to this differential equation. That's only true with this constraint. This here was the general solution to the differential equation. And this is just the first lesson with differential equations. So expect the end of this course to have some challenging aspects. But hey, it's the end.